So welcome back. In the previous part of this video, we listed out, I think, about 8 basic continuous time signals. So these are all the 8 that we listed out. So in this part of this video, we are going to be looking at each and every one of them. And like I said, we are going to be looking at the mathematical expression and what the diagram actually look like for each of these basic time continuous time signals. So if you are new here, please take our time to click on that subscribe button, or if you are yet to subscribe at all, you find the subscribe button somewhere here on your screen, a red box with subscribe on it. Kindly click on it to subscribe to the channel. Alright, so thank you very much if you have just done that, and if you have just subscribed, just let me know in the comment section and then I'll reply to you personally. Alright, so now let's look at the first one. The first one we're going to be looking at is the unit step function. So that's the unit step function. Alright, so for the unit step function, we can have it like this. So that's u of t is equals to 1 for t is greater than 0, and then we have it as 0 when t is less than 0. So this is the mathematical expression of what a unit step function is. So now let's look at what the diagram will look like based on this. Remember, the diagram of all of this function will be determined by the mathematical expression, which is this exactly. So now let's continue. So based on what we have here, so we're going to be having something that looks like this. Okay. So here is going to be our t. Exactly. So now let's analyze this. So at 1, so let's just take this place to be our 1. Then t is greater than 0. So that means we're going to be having continuously a line like this. Exactly. Then when it is 0, 0 is at this point. Our t is going to be less than 0. So there's nothing to indicate there. Exactly. So we're going to be having our u of t. So this right here that we're having here is the diagram representing the unit step function. Exactly. Alright, so now let's look at the second one. Also, the second one, which is the unit impulse function. Alright, so for the unit impulse function, we also it is also called Dirac delta function. Dirac delta function. So if you come across the word Dirac delta function, so just know that they are talking about the unit impulse function. So for this now, it is defined as d of t or delta t equals to 0 when t is not equals to 0. Exactly. So also you can also have it as the integral of minus infinity to infinity of delta t equals to 1. Exactly. So that's how it is defined mathematically. So another thing you need to also note with unit impulse function is that the area of unit impulse function is always equals to 1, as you can see it here. So it's always equals to 1, the area of units. So now for us to draw what this looks like now, based on this, if you should draw, let's draw a corner point. So this will be our t, this will be 0.0. So for this now, this is just how it will look like. It indicates from 0.0 upward like that. So this will be our d of t. So this is the diagram representing that of unit step function, and what we have here is just the mathematical expression for it. Alright, so let's go to the third one. So for the third one now, we are looking at the rectangular pulse function. So let me write that. The rectangular pulse function. So for this is defined as, so when we have our x of t, so our x of t is equals to, so if you have 1 and then magnitude of t is less than or equals to t1, then when at 0 is greater than t1. Alright, so now let's draw the figure representing what we're having here. So let me introduce the cardinal point here. So this is our x of s of t. So this will be our t. So we're going to be having something like this. So here this is going to be our minus t1, and this is going to be our t1. Here is our 0, and then here is our 1. So this is it for the rectangular pulse function. There's nothing really much in all of this that we are doing. So now let's look at the fourth one, which is the ramp function. This is a pretty popular one. So for number 4, so for the ramp function, so the ramp function is written as this. So for ramp, we have it as r of t. So some of these things are things that can also let you to know what kind of function is it. Once you see r of t, you should know that it is ramp function. If you should see, what's the other one? U of t. When we look at u of t, you know that, oh, this is a unit step function. So sometimes, and then if you see the delta, you know that, okay, that's a Dirac. So sometimes this thing can also help you to know, okay, this is kind of signal I'm dealing with. So for the ramp function, it's giving us r of t is equals to, that is 1 at t is greater than 0. I hope you can see that. At t is greater than 0, and then 0 at t is less than 0. Okay, so it can also be written as so. So let me just, which can also be written as r of t is equals to t u of t. Exactly. All right. So, okay, maybe I'll talk about this. So let's just look at some properties of ramp function. So properties of ramp function. So number 1. So r of t is equals to the integral of minus infinity to infinity u of t. Remember what u of t is, and the t. U of t is, that's unit step function. So what this is trying to say is, so that is, so when integrating, so let me just write it down. So integrating unit step function will give ramp function. Exactly. So once you integrate a unit step function, integration of unit step function will give you a ramp function. So that's what one of the properties that you might also need to take note. Then number 2 is r of t. So when you say r of t, that means the ramp function is not equals to e. So what this is saying is that ramp function is not even. Exactly. So a ramp function is not even, so that means is not even. So you can also write this as, so the even we are talking about is the even signal. So when we talk about even and odd signal. So we've talked about it in previous video in the course of this lecture series. So if you missed that, you can just check the playlist on signal and system, and then you'll find the link to those videos. So you can also write this as r is not equals to is not equals to e. All right. So the third one. So the third property I just want to mention is r of t. So that means ramp function is neither, is it NEI or NIE? It's neither NIG or power signal. Exactly. So what the third one is saying is that a ramp function is not an energy signal and is not also a power signal. Exactly. So we've talked about energy and power signal in the past. So you can also check the playlist to know what that is all about. So these are some three properties you might also need to take note. All right. So we've given the mathematical expression of what ramp function is, which is this. Exactly. So now let's just draw the diagram representing what ramp function is. So let me draw the x and y axis, which is our t and our r of t axis. So it's going to look like this, and then here this is our t, and then this is our sorry, I wanted to write x of t, but we're going to be having r of t because we are dealing with a ramp function. So this is just from point 0 like this. Okay, so this is what our ramp function actually looks like. So in this video, we've looked at 4 of the basic continuous signal. We still have 4 more to go. So the other 4, I'll continue that in the next video. So if you have any question with the 4 that we've talked about so far, do let me know in the comment section. And if you find value in it, please don't forget to give it a thumbs up. And then I'll see you all in the next one.